And I'll be kind of moderating this event this afternoon, and appreciate you all being here. We wanted to make this fun and interactive, so please chime in with any questions you may have. Intel's been coming out with a lot of new products and has plans to come out with new products here in the new year. We're proud to be covering today an introduction to Intel Optane Data Center Persistent Memory. And with us today is our presenter, Usha U, and she's a technology evangelist in our data center team. Basically, she is the one of the main evangelists for our Intel Optane Data Center Persistent Memory. So, Usha?
Thank you, Tom. Can you guys hear me? So I'm really excited to share today the groundbreaking technology innovation from Intel. It's called Intel Optane Data Center Persistent Memory. I've heard in some of the sessions this morning and this afternoon, software really referring to this persistent memory coming and how they're trying to adopt to a persistent memory, basically doing load store access instead of block and things like that. So this session is all going to be about introducing Intel's Optane Data Center Persistent Memory and what Intel is really doing to enable the software ecosystem. So today we are already shipping some of the product to some of our select customers, but it will be broadly available in the first half of 2019 and on our Intel scalable processors coming up in 2019. I think this audience clearly understands the need for larger data capacity, memory capacities, because you want to be able to load large data sets that are being generated through either traditional HPC workloads or AI and IoT kind of workloads, and along with having really high performance storage. So I'm really happy to introduce here that Intel is coming up with some disruptive products that actually help in enabling these kind of workloads. So two products that are being developed based on Optane memory that actually sit between the memory and storage capacity. There's a larger gap that we have today between storage and the DRAM. So the products that Intel is coming out with Optane based on Optane memory are going to fill the gap, and which is really, really needed at this point. So the Optane Optane Data Center Persistent Memory is going to be the main focus of this session, but there is also a block-based Optane-based SSD, and that still sits on the PCIe bus, but it's enabled with NVMe protocol, but it's much, much better performant than the NAND SSDs. So what I'm going to do is I'm going to give a very high-level overview of the features of the Intel the Optane-based persistent memory, and then we're going to talk about what are we really doing with respect to, are we developing open source enabled libraries for applications to pick up and get started on these persistent memory and things like that. So just to give high-level features of Optane DC Persistent Memory, this product is available or will be offered in 3 different capacities at the time of production, and that's going to be in 128 gig, 256 gig, and 512 gigabytes. So if you have a single socket system and if you have larger capacity DIMM that is populated on the system, you can get up to 3 terabytes of capacity. So this particular product can also be configured in different ways. So this can be configured as totally volatile capacity, or it can be configured as a completely persistent memory capacity, or it can be configured as something that you can work in terms of blocks. So it can be memory-like DRAM, or it can be persistent memory-like, which you can do load store access, but the data is persistent and much closer to the CPU. Or you can do block size I/O, but again, the device is actually sitting on the memory bus, unlike traditional storage devices that are actually sitting on PCIe bus. So I think with that, what we can talk about next is the modes.
Yeah, so that's a great segue there, Usha. Everybody's asking about the memory modes and app direct mode, so why don't we go ahead and tell the audience about that?
Yeah. So Optane data center persistent memory can be operationally configured as two different modes. Again, we talk about app direct mode and memory mode. So before we go into really talking about what modes do and all that, I want to make sure I clarify that these devices will be available on platforms that do have DRAM populated. So these will never exist by themselves. So the platforms will always have DRAMs along with these data center persistent memory modules. So a mode really, what it determines is the kind of features and capabilities that software can actually access from these particular modules. So when you talk about, I'll talk about memory mode first and then go into the app direct, but because it's very easy for adoption. So what memory mode does is, so we have configuration tools already created. So when you configure a platform that has Intel Optane data center persistent memory modules in memory mode, what happens basically is that all the capacity that you have with this persistent memory module becomes the actual memory for the system. For example, we have, let's say we have 1.5 terabytes of Optane DC persistent memory on the system, and we have, let's say, 192 gig, just some number to pick, of DRAM on the system. When you configure the system in memory mode, all that the applications see is 1.5 terabytes. The DRAM capacity is totally controlled by the memory controller. So applications never get to see or have any control of data placement into the DRAM capacity. So DRAM at this point in that particular configuration acts as front-end cache to this larger volatile capacity, which I was giving as an example of 1.5 terabytes. So if an application requires larger memory capacity, this is the way to go. Again, there are different ways of populating, persistent memory ratios with DRAM, and there's a lot more to learn about that. But at a very high level, it allows applications to have access to larger memory capacity. The best part with that is, again, it's ease of adoption, meaning you don't need to make any changes to your applications. You don't need to have any changes into your operating system or the file systems. It's almost a plug and play. You have the platform, you have your application run, and you have access to your large memory capacity. So that's the memory mode, again, at a very high level. App Direct. App Direct is something that you can configure in two different ways. So App Direct, when you can configure it as persistent memory, meaning you can do load store access, or you can also configure to be in a block mode, meaning you can have your application still do block I/O and be able to sit on the memory bus, so you have the lower latency than compared to doing the same storage I/O on a SSD that's actually sitting on a PCIe bus. So the advantage of block, configuring it in block, is that you don't have to make any changes to your application. You can run as is, but you need some changes in your operating system because you really require NVIDIA driver. But when you actually configure your App Direct as a persistent memory configuration, you basically can do load store access. So you have direct access to the capacity that you configure as App Direct, and then you basically have all the control of data placement. So at this point, in the App Direct mode, applications have two different sources of data placement. One is DRAM, so application now sees DRAM, and also a second source, which is now the persistent memory. So that's the advantage of having configured in App Direct, because you have much more control over your data placement. But what comes with that is you are now need to do changes in your application, because you really want to have that direct access to the capacity than what you had before, where you had data writing to page cache, and the page cache basically having to be moved back and forth into the backup storage device. But with this app direct, you basically have direct access to your data, and so you need much more responsibility when you're creating an application.
That's great information, Usha. Thank you so much for sharing that. Is there any questions from the audience right now while we...
So you're talking about the memory mode? Yeah, so memory mode is completely volatile. So it is basically working as any volatile memory as of today. So it gives you larger capacity at an affordable price, but you really are not, there's no persistent story there. Yeah.
What's the speed trade-off between that using a regular memory?
I'm sorry, can you repeat?
The question was, what was the trade-off between speed?
So on the memory mode side, if your workload is cache friendly, you actually get DRAM speeds, because you're basically putting the memory mode, the data placement is being controlled by memory controller. But again, if your data is hot and if you have it in the DRAM itself, you have DRAM latencies. But if it is not so cache friendly, you're basically getting it back and forth from the Apache, from the backend storage. So it may be higher latency.
I guess what I don't understand is, in memory mode, the memory is actually partitioned into two parts, which is memory and this other thing. Is that right?
So the entire memory is basically controlled by memory controller, and it has the control of how it moves the data. So if it is a hot data, it keeps it in the DRAM. And if it is not so hot data, it keeps moving back to the backend storage.
Power applied for it to remember?
I'm sorry?
Does it, if you unplug your computer,
Yeah.
does the memory go away?
Yes, it goes away. It's volatile memory. The entire capacity becomes volatile. Yeah, this mode, in app direct mode, it is all persistent. The data doesn't go away.
But this is the same memory.
It's the same memory. So what happens there is that in memory mode, there is a key that gets scrambled when it restarts the system. So there is a key that is associated with that capacity. And then when the system restarts, that key gets scrambled, so there's no data available. It becomes volatile-like. But it's the same media.
I think, Addison, you had a question?
Can you talk about what software tools or rules are available to handle promotion and demotion of data in and out if you have changes in the temperature of your data?
So in memory mode, applications don't have any control. But in persistent memory mode, we do have control. And I have a few slides to talk about the software.
Thank you.
Yeah.
So one of the things is that now if you look at having these large persistent memories, right? A lot of things in your processor and your OS kind of don't make sense anymore. First up is virtual memory and TLBs. So virtual memory, we don't have to. I mean, is there a way to turn off the TLBs? Because we're not going to be if you have such a large memory space, right? And you just use a flat address space, right? Why do you need virtual memory TLBs?
I think it depends on the workload and the environment that you're working on. But
Like the database engine.
yeah,
in that scenario, because it's like, have you guys looked at, shutting down the TLBs and the virtual memory?
So Intel has worked with several hypervisor vendors and database vendors. I don't have all the details, but I can talk to you after the session.
And then this gentleman had a quick question.
So the right side of memory mode, effectively the DRAM looks like a write to cache. Is that,
Write back cache.
it looks like a write back.
Yeah.
So it doesn't flush everything.
Yeah, go ahead.
So effectively, if you replace disk drives with this, you do away with DMA.
Yeah, this is DMA-able and RDMA-able, actually, sitting on the memory bus. Yeah.
Another question?
If I understand correctly, in memory mode, there's a portion of the DRAM reserved for the memory controller.
So the entire DRAM capacity is controlled by the memory controller. So DRAM capacity is not seen by the application.
So a Linux kernel, for instance, does it see some reserved
No.
memory?
No.
Does this require use of a hypervisor,
Require,
like with the Intel memory technology?
no, not at all. So when you configure through, so there is a lot of stuff that happens at the BIOS level. There is a lot of things that ACPI spec has introduced for NVDIMMs, NV table, and through all of these, when this system or the configuration is in memory mode, it basically all the software, the BIOS and others, along with the memory controller, basically make it look like the capacity of the persistent memory as the volatile memory, and DRAM is not seen at all.
And what's the minimum ratio of DRAM to?
Yeah, so we have done a lot of experiments with different kinds of workloads, like database workloads and others, and we have some recommendations. For database, we say something like 8:1, but we have others that we are happening as well. Yeah.
Ken?
Can you say something about the built-in flexibility to use the mode simultaneously?
Absolutely.
And also how you switch between them?
Yep. So what this basically means is that you can not only configure the persistent memory in just memory mode or just app direct, you can actually configure them in mixed mode, meaning you can take part of the capacity to look like memory, volatile memory, and part of it to look like persistent storage. So, for example, if you really want to have persistent storage on memory bus, so you can configure this to be in mixed mode as well. Have a question? I'm sorry? No.
You mentioned cheaper cost. I know you're not selling this yet, but is it half a DRAM or a quarter?
We did some ISO comparison, but again, I'm an engineer. I'm not a salesperson, so I don't really know
Rich,
how to.
I'll be in touch with you about that. But no, this is exactly what we wanted today, is to have this interaction. So thank you for the questions. Addison, you have another one?
Yeah.
Just to be specific then, what do you specifically mean by use both modes simultaneously?
So an application now can use memory. So when you configure as memory mode, and then that means DRAM is not seen. Then now when you configure as mixed mode, it's the memory capacity that is actually configured as memory mode will be seen as the volatile capacity to the applications. So the DRAM is totally hidden.
So you can have a 256 capacity and use 128 as basically just cheaper RAM DRAM.
Right.
And 128 as persistent.
That's correct.
Briefly go over like in the sense of how you can partition the namespace and how they become like different file systems?
Yeah, I have a slide in the backup, but let me just go through the main slides first, and then I can talk about how the persistent memory actually bubbles up to an application.
Good, great information, Usha. But really, the question for all of you and for everybody, out there that will be viewing this is, what does it really mean to the software developer?
Yeah. So before we go there, right? We've done some looking at different workloads. What is really good for memory mode versus what is really good for app direct, and again, as we were all discussing, there are workloads that require larger memory capacity. For example, we've been working with one of our open source HPC software called computational chemistry software called NWChem. What it does today is it has algorithms that actually computes a lot of integrals that are now put back and forth from DRAM to SSDs or hard drives or whatever back-end storages. But with memory mode enabled, what we are able to do is we are able to keep all the intermediates in the memory itself, and hence that's giving us much better performance in completing the algorithm than really taking a longer time to compute, put the intermediates into the back-end storage, bring them back into the memory. So we have actually seen some really good numbers coming out of that particular software. Again, you can load large model simulation, and with AppDirect, you have access to much better or lower granularity of data, and then you have much more control over the data placement, and other usages are evolving. So what does this really mean, right, to the software? So let's take memory mode. Memory mode is pretty low-hanging fruit. All that you need is a platform that has persistent memory available with DRAM, and then you configure it. We have tools available. Your system administrator is going to configure it, and then you basically put your application on, and that's it. You have larger memory capacity available. So I talked about when in AppDirect, it can be configured as not only load store persistent memory, but also block. So we call that mode as storage or AppDirect. In this mode, what you do is basically, again, configure it as a block, and the application doesn't need to change. The application can continue to do block, but what this requires is changes that happen in the operating system, basically in the kernel, and also the NVDIMM driver. So these drivers are available both in Linux and the Windows, and we have the enablement done in the Linux kernel starting 4.2, but I think the much more better versions of kernel, stabler versions of the kernels, like I think 4.10 or 12 is what we recommend. But we have enabled in both, the ecosystem actually has enabled both in Windows and Linux itself. So from adoption perspective, memory mode is easy to adopt. So what does this mean by adopting to AppDirect? This is where the software developers are trying to figure out how easy it is to adopt. So just to think about, step back and think about what does this really mean. What it really means is that the application now, very happy to have control over data placement and load store access, but it comes with certain things that they need to be aware of. First thing, data persistence. They need to be aware that application is now responsible to ensure that the data really gets into this kind of power fail protected domain. So this is nothing but, at the end of the day, when you do a write, it goes to the CPU caches, have L1, L2, L3 caches. And this is what I'm showing here is called power fail protected domain. What I mean by that is any platform that supports NVDIMMs require to support a feature called ADR, asynchronous DRAM refresh. What that means is when a power failure happens, there is a trigger that gets sent to the persistent memory to make sure the data that is in this domain gets flushed to the persistent memory. But anything above it is not power fail protected domain. That means the data can be in one of these caches and power failure could happen. So what do we do? So what Intel has done is actually has added few optimized flush commands called CLWB and CLFlushOpt. By doing these flush commands, you ensure that the data is now moved into the power fail protected domain. Now, if a power failure happens, it is protected through the ADR mechanism. So applications now are responsible to do the data persistence and ensuring that the data is now flushed to the power fail protected domain. The next thing is data consistency. Power failure happens, and you are really updating a larger data structure that is larger than 8 bytes. You need to ensure that there is data consistency by creating some sort of a transaction around it. So these are high-level things that need to be aware of. Persistent memory allocator, the mallocs now don't work because when your power failure happens and you come back up, the pointer is lost. You need to have a persistent memory aware allocator. Also, if you have memory leaks, persistent memory leak will never go away. It'll be there forever. So you need to be aware of that. There are different kinds of persistent memory errors that your application need to be aware and be able to handle it. At a very high level, these are the things that application needs to understand. So what did Intel do? Intel actually worked with an organization called SNIA, Storage and Networking Industry Association, along with a lot of operating system vendors, hypervisor vendors, BIOS vendors, and database vendors. All sorts of vendors were part of this. This particular organization created a programming model to be able to access persistent memory through this particular programming model. This is basically dependent or uses the mechanism memory mapping of the files, which is nothing new to anyone. It's been there forever, and it uses the memory mapped file mechanism. So I'll quickly go over the last on the rightmost side of the diagram. As a part of the programming model, they have introduced something called how do you manage your persistent memory, meaning how do you discover your persistent memory, how do you update your firmware on your persistent memory, how do you kind of create namespaces so application can actually use it. So the management library uses something called NVDIM driver, and so that's a part of the spec as well. The middle portion is the storage. Again, we talked about being able to configure in a block mode, and that's the storage mode that I was talking about. So the application stays as is, as before, but again, same file system, but it requires the NVDIM driver that actually understands how to talk to the persistent memory, or NVDIMs. The leftmost is what is really of interest to us, that actually enables persistent memory to applications. You see here something called persistent memory aware file system. What that actually means is that the file systems like XFS, ext4, NTFS have enabled something called direct access, DAX, it's called DAX, direct access, which understands that the system, the device that it's talking to is persistent memory aware, and it knows to be able to allow the applications to do direct load stores. So what really happens in that mode is that application says, okay, I have the file system mounted with the DAX option. So now file systems can be mounted with DAX option. Then you create a memory mapped file on the DAX enabled file system. And when you map the file, what really happens is that the memory mapped region is now gets into the virtual address space of the application. So direct access allows you to basically load the memory map region into the virtual address space of the application. And hence, you now have the ability to do load store access. So that's the basically the spec. I'm sorry? So there are we have certain tools that are available that you have some flexibility with that. So what we have done as Intel, right? I mean, now there is this association that have come up with a spec that basically talks about how you memory map this huge, you can create a 1.5 terabyte of memory mapped file. But then we really need to allow applications to be able to create smaller data structures in this persistent memory and be able to, kind of talk to it directly. So Intel came up with and created, actually contributes a lot to this open source set of libraries called PMDK, Persistent Memory Development Kit. I know somebody talked about SPDK, so it's basically along the same line. So this is a PMDK. So it created a set of libraries. At the bottom, we have much lower level support, meaning this library really understands if a particular flush instruction is supported or not, and a lot of low-level nitty-gritty details are understood about the platform. The middle layer is actually a little bit higher level that actually allows or provides capability to do some sort of a transactional operations, but in turn they talk to the libpmem or the lower level libraries. So they actually do, for persistence, they use a libpmem, but the upper level libraries like libpmem log and the obj and libpmem block are basically to doing the transactional kind of operations. libpmem log and block are really catered towards certain usages, so we have really optimized for logging purposes and or for if you really are doing applications at the block level. But libpmem obj is basically our main library we work on. That's the one that actually has improved much, performance on allocations and things like that. But again, we have several language bindings, C++, C. We have recreated persistent memory collections for Java, and we have some development going on with Python. One thing I really want to focus on right now is support for volatile, meaning we have actually added persistent memory support for libmem kind. So I think the next slide probably talks about that. Yeah. So it's really funny to say using persistent memory as volatile memory, but what this actually allows you to do is, if you want to create capacity that you really don't want to keep it persistent, right? So you want to be able to use this larger capacity for some volatile purposes. So libmem kind now can take the parameter called pmem, kind, takes as pmem. What it basically does is creates a temp file under the hood, and then you can use that, and that's memory mapped, basically, that's memory mapped, and that is given as a source of memory to underlying memory allocator. And when the application allocates memory from this volatile capacity, it basically uses as volatile capacity. When the system reboots, the temp file is gone, so it basically is volatile. So this is one of the use cases that we are seeing some of our customers, like HPC customers, actually use. So just want to showcase that libmem kind, we do have production quality support for persistent memory. Quickly, again, the ecosystem, I think we have different organizations that we have been working with, operating system vendors, and all sorts of ecosystem enablement happening right now.
And we're still working on getting a real robust ecosystem in place, and
Absolutely.
It's happening every day. New vendors are coming to us, and that's the exciting thing about this memory, is that we're kind of talking to the whole ecosystem and getting people excited about this new technology. I mean, this could be a real game changer. So we're Intel's really excited about Intel Optane DC Persistent Memory.
We have lots of resources available right now, videos, blogs, short videos, webinars. There's several links here that have available information about software, our persistent memory in the open source and things like that.
And you guys will get this presentation, so you won't need to worry about having to copy those down or take photos. We'll get the presentation.
Yeah, one other thing I forgot to put on this is we are actually introducing our very first PMDK Summit. It's going to be held on April 16th and 17th in San Jose. We also have a Google group somewhere here. So I'm going to be posting basically the event status updates. So watch out for that, and we hope you all come and listen to us at the summit as well.
So we were just going to go ahead and end up here by imploring you as the community, the ecosystem. You guys are all brilliant minds in this room, and we really would like you to take a look at this technology and say, how can I use this? How can I go beyond what's already out there being done in the memory space, and look at it really for an HPC cluster where you need that resident data really close by to be able to run the applications to the best of their ability. Because that's really what makes the difference. We're seeing this already happening in the artificial intelligence, simulation, modeling, visualization space, health and life sciences. And we're basically asking all of you to think about this outside the box and really unleash the next wave of innovation. So thank you very much for your time. And Usha, thank you. Great presentation, great information.